everybody! So today we're going to talk a little bit about moles and just do some very basic stoichiometry involving moles. So what is a mole? Well, in chemistry, it's a method of counting the number of atoms that you have in a sample. Because atoms are so small, we need a really big number to represent a certain amount of atoms. So, and I always use this example, but when you go to Dunkin' Donuts, or you go to the bagel store, you'll say, I'll have a dozen donuts, or a dozen bagels, or a dozen donuts. We use that word dozen to represent a certain number, and that number is 12. So when you go in there and say, I'll have a dozen, they know you mean 12. However, in chemistry, we need a number that's significantly bigger than 12, and that's because atoms are significantly smaller than bagels or donuts. And we use the word mole, and 1 mole represents 6.02 times 10 to the 23rd. So that's 602 with 21 zeros after it. And if I'm remembering correctly, I think the word you use to represent that is a sextillion. If you had me for Chemistry 1, you probably did the Great Mole Project, and if you had, just from my example, if you had a mole of pugs, which you probably hear him barking because the mail lady was just here, you can go back and forth to the North Star with 1 mole of pugs, or 6.02 times 10 to the 23rd pugs, over 50,000 times. That's a lot of times, the North Star here and back. So that number is huge. And that just goes to show really how small atoms are, because if you had 6.02 times 10 to the 23rd grams of carbon, that carbon would weigh about 12 grams. So if you think about it, if you had one pencil contains lead that's probably not a mechanical pencil, but a regular pencil, probably has a piece of graphite inside that's almost 1 mole. So that would contain the same number of atoms that it would take to get back and forth to the North Star with a mole of pugs over 500,000 times. So really big number. And of course, because atoms and different elements on the periodic table contain a different number of protons, neutrons, and electrons, they are going to have different masses per 1 mole. So if I have 1 mole of hydrogen, which only has 1 proton in the nucleus, that's going to weigh much less than, let's say, 1 mole of carbon, which would have 6 protons in the nucleus, plus quite a few neutrons in there as well. Depending on the isotope, probably about 6. When we're converting from moles, we do have to keep that in mind. We have to use the molar mass of a sample, which we can find on the periodic table, and we also have to consider that 1 mole of any material contains 6.02 times 10 to the 23rd particles. Let's go ahead and do some examples together. So when we're doing mole conversions, this is basically how the mole conversions are always going to go. In chemistry, everything relates back to moles. So when in doubt, mole it out. If you don't know how to do a problem, always convert to the number of moles first, because you're probably on your way to solving the problem correctly. When I want to convert mass to the number of moles, and of course mass is going to be in units of grams, we have to use the periodic table and look up the molar mass. And molar mass, don't forget, is always in units of grams per 1 mole, or just grams per mole. So we'll do a couple of examples with those together, but you do want to look at the periodic table. I'm not a memorizer, so don't memorize, I divide by molar mass here, I multiply by molar mass there. Use the molar mass, set the problems up the way I show you how to set them up. That'll tell us the number of moles from mass, or vice versa. If you want to convert to the number of particles, and a particle could be really anything. It could be atoms, it could be particles themselves, they could be molecules, formula units, which I'll just abbreviate to F units. They could be basically anything. But to convert from moles to the number of particles, we need to know that 1 mole of anything contains 6.02 times 10 to the 23rd of that thing. So in this case, it would be 1 mole of particles contains Avogadro's number of particles. 1 mole of formula units contains 6.02 times 10 to the 23rd formula units. There's nothing different between doing conversions there. Using stoichiometry, we've done mole conversions, going from moles of one reactant or product to moles of another reactant or product. Later in this video, I'm going to take that a step further, actually, because I always tell my students if they're taking a chemistry class, let me know if you have any questions on anything. And the most common question I get is this one specific type of mole conversion, and it's actually very simple. So I'm going to show you how to do those, and you'll have a couple practice problems on the corresponding worksheet and also in the problem set for the first chapter we do in class. Let's do a couple of examples together. So for this first one, we want to convert 3.9 grams of neon to moles of neon. We always want to start off with what we're given. You're going to see me write the formulas here for now. You don't have to do that all the time. In problem sets I will. Sometimes on the board I'm not going to do it, but I will in here just to keep things nice and organized. So whatever unit's up top, just like in dimensional analysis, I'm going to bring that down. And let's convert that to moles of neon. Because we're converting the mass, or the amount of grams, to the number of moles, we do need to find the molar mass for neon. And if you look on the periodic table, the molar mass for neon is 20.18 grams per mole. So what does that mean? Technically, that means that 1 mole of neon has a mass of 20.18 grams, where 1 mole is also equivalent to 6.02 times 10 to the 23rd atoms. You don't need the number of atoms for this particular problem, though, because it's not starting you off with atoms, and it's also not asking you to convert 2 atoms. So this number doesn't mean anything to us, but that's what the 1 mole part means, is that 1 mole of neon, which is 6.02 times 10 to the 23rd atoms, has a mass of 20.18 grams. Make sure you plug your values in next to the correct unit. So 1 mole has a mass of 20.18 grams. Those units mathematically cancel. And I will solve and get 0.19 moles of neon. Always plug your units in. And that's the first one. Let's try a second example. This example, we're going to start off with the number of particles. In this case, the particle's the molecule, because I have more than 1 atom bonded, so it has to be a molecule. We'll convert that to the number of moles. So, always start off with what I'm given. Molecules of SO2. Try not to abbreviate the word molecule, because sometimes I notice students do that and then they get confused and they think it's a mole, but a mole is very different from a molecule. So I would highly recommend using the whole word molecule for this. Let's convert molecules to moles. Now here we don't need to find the molar mass for sulfur dioxide, because we're going from the number of moles to the number of particles. So we don't need to find this. And I find a lot of students start to do unnecessary math when they don't need to. All you need to know is that 1 mole of anything contains Avogadro's number of particles for this particular example. So 1 mole of SO2 contains 6.02 times 10 to the 23rd molecules. So when I solve that, I get 0.00168 moles, which you can leave it like that, but I'm going to convert it to scientific notation. Oh, move that over there. We have 1.68 times 10 to the -3rd moles of SO2. If you are unfamiliar with converting in and out of scientific notation, which is really important in AP chemistry, I would watch the scientific notation video that I also have as a crash course, just so you get familiar with converting back and forth. Let's try one more, slightly more complex example. So let's convert 0.02 milligrams of aluminum bromide to formula units. You'll sometimes see units of milligrams, kilograms, or something that's not in units of grams. If you want, you can just move the decimal point as long as you're comfortable and you do that correctly. I usually just like to throw another conversion in there and just do it all at the very end. So here, notice I'm not going to or from moles, but I do have to pass through moles because that's what relates the mass of a sample to the number of particles. So we're going to convert milligrams to grams first. We're going to convert grams to moles, and then moles to formula units. 0.02 milligrams. Now, like I said, you can just move the decimal point. I don't know, I just always like to plug another thing in here quick. There's 1,000 milligrams in 1 gram. So those units cancel. Grams of aluminum bromide to moles. Aluminum bromide. Now, unlike above, where you can just look at the periodic table and find the molar mass for neon, which is what we did up here, this one you do need to calculate. So this particular problem has 1 aluminum atom bonded to 3 bromine atoms, so you do have to add the total mass for all of those atoms together. And when you do that, you should get 266.68 as the molar mass. So that means that 1 mole of aluminum bromide has a mass of 266.68 grams. Then, those units canceled. Let's convert moles to formula units. The reason why it's a formula unit is because technically this is an ionic compound, and ionic compounds, we really don't call them molecules because they don't form Lewis dot structures, they form crystal lattice structures, and therefore it's really not a molecule, but it's a simplest ratio. There's a lot of chemistry that goes behind that, which we're going to talk about later on in the course. But because it's ionic, it's a formula unit, but it's the same exact math. 1 mole of anything, in this case aluminum bromide, contains 6.02 times 10 to the 23rd formula units. And when I type all of that in the calculator, I get an answer of 5 times 10 to the 16th formula units. And it's a pretty big round because on the calculator I have 4.5 times 10 to the 16th. But this original number only has 1 significant figure, so my answer should also have 1 significant figure. There's your super basic example of just regular mole conversions. Let's go ahead and review stoichiometry really quickly. Now, in chemistry, of course, mole conversions are important in themselves. However, what's more important is using stoichiometry to convert the mass or the number of moles of one reactant or product to the mass or number of moles of another reactant or product. And in chemistry, that's really where you're going to use all of your mole conversions. Is you're going to be given a reaction, you might be doing it in a lab, you have a certain number of grams of a reactant, and you need to figure out how many grams of a product can you make from that mass of that reactant. So this is really where mole conversions is the most convenient and the most used. Let's go ahead and do those examples together. So here's a really basic example of just some reaction. I have hydrogen gas reacting with oxygen gas to produce water. And I did in fact balance this. You don't always have to put the 1 in front of your reactants or products if that is its coefficient. I am just in the habit, I always put a 1 there. I don't know, I think it looks more complete that way, but you don't have to do that. Looking at just a balanced equation for some reaction tells us a lot of information about how much reactant or product is going to be needed or formed from another reactant or product. So let's just do one without any math here because we don't always need to use math. Let's say that I have 5 moles of hydrogen that's in this reaction. I have 5 moles of hydrogen. How many moles of water can I produce from 5 moles of hydrogen? Now, you can do math for this. There's nothing wrong with that. However, let's just look at the coefficients of the hydrogen versus the water. According to this, now let's break it down even more. 2 molecules of hydrogen will produce 2 water molecules. However, in chemistry, you're never just dealing on a molecular scale. You're dealing with, moles and moles and moles of molecules. So here, instead of using just atoms, if we say we have 5 moles of hydrogen reacting, and look, the coefficients are exactly the same number of moles of water can be produced from some number of moles of hydrogen. So in this case, you can produce 5 moles of water from 5 moles of hydrogen. And that's because the coefficients are the same. Let's think about oxygen here. So again, if we think on a mole level, well, if I have 2 moles of hydrogen, I need 1 mole of oxygen to react with that to produce the water. So if you look at the ratio, I have half the amount of moles of oxygen needed to react with all 2 moles of hydrogen. So therefore, if I'm given 5 moles of hydrogen, what's half of 5? Should be 2.5 moles. Now you can do this with stoichiometry and actually setting up your problem, but for an example that's as easy as this, you don't even need to do that. You can just look at your mole ratios and just do the work accordingly like this. Let's do one example with some math, however. So let's use this equation here. So I have these compounds. I'm not 100% sure how to name these off the top of my head, but that's okay. Sometimes you will need to balance an equation first. If you're really lucky, you might have to write the equation, but in this case, we're just going to balance this quickly. Just a quick review on balancing. Let's write it in a different color here. I have to have what's going in, the number and type of atoms must be equal to the number and type of atoms going out on the other side. I always like to balance hydrogens and oxygens last, so let's do boron first. Looks like I have 2 and 1, so let's throw a 2 in front of there. Let's do hydrogen next, because I know that this guy here is already balanced. So I have 6 hydrogens going in, I have to have 6 hydrogens coming out. Here I have 2, and here I have another 2. So let's add 2 water molecules, so I get a total of 6. 2 times 2 is 4, plus another 2 is 6. That equals the 6 over there. One of my tricks is I sometimes like to do check marks above just the reactant side, so I know it's balanced. Now let's balance oxygen. Another common mistake I see is students forget to add the total oxygens together, because sometimes you might have an element that's in more than one product or reactant, so just keep that in mind. 2 groups of 2 is 4 oxygens, plus another 2 here is 6. How many groups of 2 gives me 6? That is going to be 3. So there is our balanced chemical equation, which we need in order to do this stoichiometric problem. So let's see, what mass of oxygen will be needed to burn 36.1 grams of diboron hexahydride. That's the complex way to name that, but I'm almost positive that has a more simple name, which I can't think of what it is right now. Just like with a regular mole conversion, if you're given something in units of grams, you always want to convert it to moles first. So let's start off with grams. And grams of this compound here. This is where it comes in handy to write the whole entire formula out, because sometimes students get confused about which reactant or product they're working with. I think it's useful to do that here. Let's calculate the molar mass, because I'm relating grams to moles. And the molar mass is 27.68. So 1 mole of that compound has a mass of 27.68 grams. Now that I'm in these units of moles, that's where I can bring this particular compound and relate it to my other reactant. Because just like I showed before, 1 mole of this compound here needs to react with 3 moles of oxygen in order for this reaction to go to completion. So these numbers are what we're going to use to relate these two reactants to one another. Whatever unit's up top, I'm going to bring down. And let's relate that to moles of oxygen. And if I look at this balanced equation, 1 mole of this compound will react with 3 moles of oxygen. Now that I'm in moles of oxygen and you want to know the grams of oxygen, that's easy. That's just a regular old mole conversion. 1 mole of oxygen, it's diatomic, so it's not 16, it's 32. And you should get 125 grams of oxygen. Doesn't get more complex with that with stoichiometry. If you have the reaction, you need to balance that reaction and use those coefficients in order to relate both of your reactants or products or one of each to one another. We're going to do limiting and excess reagents and percent yield in class again, just as a refresher, because I think that can be a little confusing sometimes, so I do want to do that in person. But these basic stoichiometry problems, they're not going to get much more complex than this. The only way they might is if you're starting off with milligrams or kilograms or something like that, because you do need to convert it to grams first. Otherwise, it's always grams to moles, moles to moles, moles to grams. These next types of problems I don't teach in Chem 1 or Chem 2 because you really don't see too many examples in textbooks or in worksheets with these. However, I usually tell my students before they start their new chemistry classes in college, oh, let me know if you have any questions and I'll help you out. This is probably one of the questions that I get asked very early in the new school year is, I guess college professors really like to do these types of problems and students generally have a hard time with them and they're really not that hard. So I'm going to show you how to do these really simply, and you're going to see a couple of examples with these in your textbook and also in the problem set and maybe in some worksheets that we do in class. You'll also see some and the corresponding worksheet for this particular crash course video. But they're really simple, so I figured why not take a few minutes and just show you how to do these really simple mole conversions that professors seem to really love that give students a hard time. Let's do some of these and then we'll be finished with this crash course. So before we get into a problem, let's just look at this formula here. So I have water, right? Dihydrogen monoxide, hydrogen hydroxide, however you want to say it. If I take a look at this 1 water molecule contains 2 hydrogen atoms, and it also contains 1 oxygen atom. That's really all you need to know how to do these types of problems. However, just like in mole conversions, we don't ever work on the atomic level. We're always going to work with the number of moles. So, if I have, let's try this in a different color, 1 mole of water molecules, so 1 mole of water molecules, 1 mole of water molecules contains 2 moles of hydrogen atoms, and it also contains 1 mole of oxygen atoms. Okay? That's the very basic breakdown of something like this, is it's always coming back down to moles. We can say atoms and molecules, 1 molecule contains this many atoms. Technically speaking though, like I said, we never work on the atomic scale. We're always going to work in units of moles. So 1 mole of water contains 2 moles of hydrogen atoms, because there's 2 in every 1 molecule, and 1 mole of water also contains 1 mole of oxygen atoms. if you want, you can also say that 1 mole of oxygen contains 3 moles of total particles or atoms. I think on your worksheet there's a problem like that, so just be careful. That's the basic idea behind something like this. So using this, let's just make up a problem here. Let's say I have 1.02 grams of water. We want to know how many oxygen atoms are in 1.02 grams of water. We're going to start this off the same exact way because when in doubt, mole it out. We're always going to convert to units of moles. 1.02 grams of water. Let's see, grams of water to moles of water. The molar mass of water is 18.02. Now that I'm in moles of water, like I showed before, up here, we can use these relationships. 1 mole of water contains 1 mole of oxygen atoms. So here, whatever unit's up top is what I'm going to bring down. And I'm going to convert that to moles of oxygen. 1 mole of water contains 1 mole of oxygen. It's a 1-to-1 ratio. Now that I'm in moles of oxygen, which is just oxygen, which is what I want to work with, I can convert that to atoms. Now notice I always plug the units in first, and here is also where it's important to write the formulas with it, because again, students can get a little confused if they're not there. So moles of oxygen to atoms of oxygen, 1 mole of anything contains Avogadro's number of things. So when I solve this, 3.41 times 10 to the 22nd atoms of oxygen. So the only new step we really added is this guy right here, which this isn't really a new step because this is also a mole ratio, which is what we're using in regular stoichiometry problems. But in this example, we're not going from one reactant to another reactant or product. We're going from the whole entire molecule to what's inside the molecule. Let's try this one. So it's a little bit backwards from what we just saw, but really, if you have that mole ratio, that's the only thing that's new. So here, I started off with grams, so I use the molar mass first. Here, I'm starting off with formula units, so I have to use Avogadro's number first and to convert that to the number of moles. So let's go ahead and start this guy. Always convert to moles first. So we want to know how many grams of oxygen can I isolate from 9.0 times 10 to the 21st formula units of this compound. Again, I don't know the name off the top of my head, but that's okay. Formula units to moles, and that's in, oops, Na. Same unit. And we're going to use Avogadro's number first. 6.02 times 10 to the 23rd. Now that I'm in moles of, I think this is thiosulfate. Okay, it was what I thought it was. This is sodium thiosulfate. Makes it a little bit easier. So, moles of sodium thiosulfate to moles of oxygen. And here, if I look at this formula, 1 mole of this whole entire sodium thiosulfate formula unit contains 3 moles of oxygen. You have to look at the subscript to find that out. Once you're in that unit of moles, now you can convert to anything. Because I want the units of grams, let's convert moles to grams. Moles of oxygen to grams of oxygen. Now notice here I'm not using the diatomic. I'm just going to the element oxygen. So you're going to use 16. You only want to use the diatomic if you're doing a reaction that actually has a diatomic oxygen. So let's say I'm decomposing mercury to oxide. Oops. You're producing oxygen there as one of your products. So that's when you're going to use diatomic oxygen. Here it's just the element oxygen that's in the compound. And your answer should be 0.72 grams of oxygen. Like I said, these types of problems I notice usually give students a hard time, but it's just using this mole ratio step, just like we were before with stoichiometry. If you have any questions on this, let me know. In Chem 2, we did go over lots and lots of stoichiometry, and you should have been good at mole conversions by then. In Chem 1, we did lots of mole conversions, so really the only new step for you to learn is the mole ratio step. As always, seek me out if you have any questions. Try the corresponding worksheet. Take a look at the answer key just to make sure you have this stuff down. I will see you guys in the next video.